can be part of the exam, it is always my duty and responsibility to ensure that I explain the basic concepts. So we will not be doing any activities today. We'll do activities tomorrow. However, I am going to try and say, if you have a textbook already, that textbook is talking a lot of things. It will take you 20 days to finish this particular chapter. So we are going to finish it hopefully tomorrow. Everything that has to do with this. But we are going to expose ourselves to exam type of questions as part of practice. By the time you go to school Wednesday, believe you me, you will be in a position of answering everything that has to do with momentum and impulse. But as you normally know, ladies and gentlemen, we usually start everything with a definition. So the question is now, what is this momentum? Ladies and gentlemen, momentum is defined as a product of mass and velocity of an object. So keywords here: product of mass and velocity of what? Of this particular object that I am having. So what does this say? It says to me, then mass, I know it is a scalar quantity. However, I know that velocity is now a vector quantity. What does this now say to me in terms of momentum, ladies and gentlemen? It says to me, momentum now must be a vector quantity. Why must it be a vector quantity? Because momentum, ladies and gentlemen, it will have now what? Both magnitude and direction. So there is no way you can refer to momentum and not refer to the magnitude and the direction thereof. Why? Because velocity, as being a vector quantity, it overcomes the mass as a scalar quantity. And already from a definition, we can generate a formula of how to calculate momentum. The formula to calculate momentum is P is equals to mv, small p, ladies and gentlemen, where now P is just momentum, and then m is now the mass, and then v is the velocity of the object. So this is already now what? A formula number one that I need to apply when referring to momentum. Fine. Now what else can one say about momentum? One can easily say, but now what will be the SI unit of this momentum? The SI unit of mass is kg. The SI unit of velocity is meters per second. So the SI unit, ladies and gentlemen, of momentum is kg meters per second. That is now the very first SI unit in grade 12 that one must be able to know. Why? Because per the definition that is given, is defined as the product of mass and velocity, product being the multiplication thereof. Then it basically says, fine, ladies and gentlemen, can I be able to apply this as a form of clear understanding? 100% I can be able to do so. Let's have now example number 1. Just a basic example. I have a ball here of 2 kg mass traveling in that direction. But I am told that it is traveling in 2 meters per second. And then the question is, calculate the momentum of the 2 kg ball. First things first, we are working with a vector quantity. I need to tell the examiner to say I am taking right as positive. You need to do that. Why do you need to do that? Because we are working with velocity, we are working with momentum, both of them being vector quantities from grade 11. They must have the both magnitude and now the direction. So before I can attempt to do this particular problem, ladies and gentlemen, choice of direction is very, very, very important. Choice of direction will be very, very, very important. So remember, in all the questions that we are going to attempt to do, choice of direction is critical. Why? Because we are working with vectors. Please, please, please. Now, let's do it by so doing. Then what are we having? Most people usually say write down your data. I like it because it basically puts everything into perspective. So I have the mass that is now 2 kg. Fine. Do I have V? Yes, I have V, which is 2 meters per second to the right. So what is the question? Calculate momentum. Then it's easy to say P is equals to M over V. Ladies and gentlemen, I repeat, the formulas will be given in the formula sheet. No need for you to memorize this. Take any previous question paper of grade 12, paper 1, paper 2, take out that data sheet. Always have that data sheet when you practice. Why? I have seen now during the marking session of November 2023, when we were marking the grade 12s of 2023, they lose marks only because of trying to memorize the formulas. So this question will be 3 marks, but for me to give you 3 marks, or for the marker or the examiner to give you 3 marks, ladies and gentlemen, you must attempt to substitute. And then this will give us 4 kg meters per second. If we're going to mark this thing, it will be 1 for the formula, 1 for the substitution, and 1 for the final answer with the correct SI unit. Then we get now our 3 marks for that. But ladies and gentlemen, some people will get 2, some people will get 1. Why? Because 1, incorrect formula, 2, incorrect SI unit, and also forgetting that in actual essence this thing is a vector quantity. So it being a vector quantity, it means now what? I must also add direction to say it is moving to the right. Is then that I can be able to get 3 over 3. Motewa CDD, inputs please.
I'm understanding everything so far, sir.
Thank you very much. Ladies and gentlemen, this is basic. And obviously for physical sciences, you will not get such basic question. They are going to manipulate it, make it complex, scenarios and everything. But we are going there. And us going there, it means the approach thereof should be, do we understand the basics of the basics? So momentum, product of mass and velocity. It's a vector quantity. It has both magnitude and direction. The formula will be given: P is equals to mv, the correct SI unit, such that we do not lose unnecessary marks along the way. So this is now section 1 of momentum and impulse. Let's move, ladies and gentlemen. Remember, you will get the e-notes. If you did not manage to capture everything, you will also get the link to the recording. Do not worry. Now, at number 2, most people do not explain this part. I remember when doing rounds, visiting schools, checking if the science is being taught the right way. Most people do not do this part. And this part is the part now where we miss the application of momentum. We have a section that we call a collision. Ratanang Pesho, in simple terms, what is a collision? Simple terms, basic English.
So isn't it like when something meets with actually I don't know, but like when something meets with something else. I
Yes,
don't know.
when there's contact between the two objects or something like that.
Yes,
Now, let's explain it in scientific form. In scientific form, we say a collision is an isolated event in which two objects exert a force on each other. On each other. Full stop. It is not a definition. You will not be asked this definition. It's me trying to emphasize what I'm going to say now. Now, if we have two objects that exerts a force on each other, in grade 11, we spoke that actually Newton's third law explains the mechanics of collisions. VC, please, Newton's third law, grade 11, what does it say?
Newton's third law states that when I forgot, sorry.
His Excellency, assist your fellow partner there. Newton's third law, what does it say?
Um, when object A exerts a force on object B will exert a force of equal magnitude but in the opposite direction to object A.
Thank you very much. So, for us to have a collision, it means, ladies and gentlemen, if I have a wall here, let's fill it with brown, and then I have an object, let's fill it with yellow, and this object it's moving into this direction. There will be another part. There will be another part, this part. Also fill it now with brown. Then there will be another part. Also, maybe I should just copy this one. Put it here. So there will be three things that are happening during this collision. There will be three things that are happening. Something like this. Now let's explain what is happening. You have this object that is now moving at 20 meters per second towards now what? The wall. So this section here, we call it before it hits the wall. But now here you can see it's now during the collision. Why do we say that is now during the collision? It is during the collision because, ladies and gentlemen, you have the ball and the wall now in contact with each other. So the ball will exert a force of a certain magnitude to the wall, and the wall will exert now the same force in an opposite direction to that. That is the reason why we have now the ball that will be bouncing off the wall. So now this is after the collision with the wall. So I want you to understand what is happening. First thing that is happening is I am going to take this part of during and take it up there and say, Lesedi Katadi, I want us to draw a free body diagram of all the forces acting on the ball. Maybe the question should be, how many forces am I going to get?
So I want to say just about three forces.
Three forces. Okay. Maybe let's consider only forces that are involved in making this object to move. How many forces?
So two.
Two, ne? Two.
Yes, sir.
Why? Because if this is my object, let me use black. If this is my object, I'm going to have the force applied by F of now what? Ball on the wall. And I'm going to have the same amount of force, and this will be now force of what? Wall on the ball. That is what Nakalo is saying when we say this mechanism is explained by Newton's third law. So Newton's third law is action-reaction pair. Pair means you will always have two forces when you refer to Newton's laws. Now, this is very, very important and critical, ladies and gentlemen. You will always have two forces during a collision. However, I want us to automatically say, let's take this and do what? Draw a specific graph of what is exactly happening here. Let me draw a graph of better of f max over time, and this time in seconds. Now, when the ball, we are focusing on only during, né? There are two things that are going to happen here. We are going to have compression and we are going to have expansion. Bonolo Matosa, in simple terms, compression.
So I would say compression is like when something is
Simple English.
yeah, like something is becoming tighter, like it's going inwards. Inward
Yes.
movement. Yeah.
Thank you. Now let's consider this ball of ours. Let's call this ball something like a tennis ball. So this tennis ball, when it hits the wall, before it can actually change direction, it now squeezes itself towards the wall. And that part, ladies and gentlemen, we call it now this section here. And this section, we call it now compression. Why compression? Because we have now your maximum force being applied to this particular object. But the object is going to leave the wall. So the wall will not be exacting that same amount of force. Why? Because now the object will be expanding and moving away from the wall. What is going to happen to that F maximum? Ladies and gentlemen, that F maximum will now decrease. And this part of decrease is the section that we call now expansion. So please understand, when the object is hitting the wall, we have that compression. The compression, ladies and gentlemen, takes us now to what? Takes us now to the F maximum that now the object will be able to experience. So this time here, ladies and gentlemen, is what we call contact time. Contact time. And this contact time is now what? During the collision. That is now the contact time. During what? During the collision. Where is the collision? When the object or the tennis ball actually hits the ball. Ratanan Pehlo, input please.
So far, understand, sir.
Thank you very much. Now, ladies and gentlemen, there are a lot of things happening here. The force is decreasing because the object is no longer in contact with the object. So here we say contact begins, and here we say contact ends. Contact ends. Fedil. But what does this say to me? It says I now have PI. What is this PI? PI is momentum before. And I'm going now to have PF, which is now momentum after. Why? Because now I have two different scenarios that are taking place. Scenario number one, the object approaching the wall. Number two, the object moving away from the wall. But there's this part of the collision during, and that it is explained by Newton's third law. The graph, ladies and gentlemen, is very, very important. You'll come across questions where this graph was asked, but we could not be able to answer that particular question. Why? Because, ladies and gentlemen, this section is not explained in detail. So remember Newton's third law, the graph, a compression and expansion, there's momentum before and momentum after. That is now during what? A collision. So you must ask yourself, when there is a collision, Newton's third law applies. And if there is a collision, it means I must have now what? The momentum before and the momentum after. Why? Because a collision, we are saying, is an isolated event in which two objects exert a force on each other. So by exerting a force on each other, the possible changes in direction, the possible changes in velocity will still now be applicable and be applied in the calculations thereof. Ladies and gentlemen, most important part is that during a collision, let's say that during a collision, let's consider two cars. How can you tell that there was an accident when you are sitting inside your house? Maybe by the robots next to your house. If
So I, when you say how do I tell, like,
how can you tell that there was maybe an accident just maybe next street?
I'm going to say, next week I'm going to say sound.
Sound, ne?
Yes, sir.
And then when you get to the cars, when you are trying to assist, what else is there? What do you see? Do you see smoke? What else do you see there?
Yes, smoke, I also see damage to the cars.
Damaged cars and smoke and people injured and everything like that. Ne?
Yes, sir.
Thank you. That thing, we call it, ladies and gentlemen, energy is lost. And this energy during the collision that is lost, it is lost in a form of heat and in a form of sound. Some people will add rain cages and everything, breakages of the windows and everything, but the key ones, because we refer in our syllabus heat as energy, sound as energy from grade 10. So this part is also very, very important. So during a collision, energy is lost. It's lost in a form of heat, it's lost in a form of sound. Very, very, very important. But when energy is now lost, in grade 12 we say energy is not conserved. Very, very, very important, ladies and gentlemen. Energy is not conserved. His Excellency, inputs, suggestions, please.
I'm still good, sir.
If you are good, then it means we can go to the other section of this particular topic. This section, ladies and gentlemen, it's number 3. It is called now change in momentum. Change in momentum. Change in momentum, we say if the velocity of the object changes, the momentum will also change. The momentum will also change. Is it true? Yes, it is true. Let's quickly go back to this one. Because of the energy that is lost, we will say maybe roughly this one will be now traveling at 15 meters per second. 15 meters per second. What is the mass of the tennis ball? We say the mass is given as 0,057 kg. Remember, if the mass is not given in kg, ladies and gentlemen, you must convert the mass to kg. Very, very, very important. Now, we have the momentum before and we have the momentum after. Let's try to do that. I'm just going to say P initial. We all know how to calculate momentum now. 0,057 kg. It is traveling now with 20 meters per second. And what did we say? Write as positive. Fine, I'm going to calculate it quickly. 0,057 multiply by 20 gives me something like 1,14 kg meters per second to the right. This is now that object of ours. But after hitting the wall, P final, after hitting the wall, P final also NV is the same object. Yes, 0,057 multiply by 15, but we said it must be now a minus 15. Why, ladies and gentlemen? It is moving away from the wall. Then I'm going to just say 0,057 multiply by 15. This will give me something like negative 0,855 kg grams per second. There's a rule of thumb that says you must not leave your answer as negative. Then you can just basically say P final is just 0,855 kg meters per second to the left. But what was the question? There was no question. It is me just now emphasizing the momentum before and the momentum after. Now the question comes to say calculate the change in momentum. So So the change in momentum, ladies and gentlemen, it will be change is equals to P final minus P initial. And this now becomes easy because we have 0 minus 0 comma 855 plus, okay, minus 1 comma 14. Then this is basically just saying plus 1 comma 14, and then you get something like is equals to 1 comma 995 kg meters per second. And this is now our final answer. So change in momentum is just the momentum before, the momentum after minus the momentum initial. So you must be able to perform such calculations. All these things that we are doing, ladies and gentlemen, it's a build up to more complex problems that we are going to do. Then we can immediately say, using the very same information, we can introduce ourselves now to a vector diagram. And vector diagrams of momentum vector diagrams. So these are now basically focusing on momentum vector diagrams. Why momentum vector diagrams? It is a vector, ladies and gentlemen. It is a vector. Now let's draw this vector. It was moving to the right. Here is the object. It is moving to the right. Fine. And what can we say? It is easy. This thing is just a plus 1 comma 14 kg meters per second. What happened after collision? There is the object. It is now moving in an opposite direction, but with a smaller magnitude, because it is now what? 0.85 in an opposite direction. Let's also make it black, and then we label it now. This is just 0.855 kg meters per second. Sorry. Now, ladies and gentlemen, we must get the change in momentum. Because of the signs negative, 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 it means now I'm going to have to combine everything here into this direction, because now it must be the sum of the two, and this now will be my 1 comma 995. Oh, sorry, it is negative. Let's change the direction. It's negative, negative, so it will start there and then move into this direction. It will be longer. The reason for it being longer, its magnitude is now almost 1,995 kg meters per second. And then it makes a lot of sense to say, yes, this is now P initial, this is now P final, and this is now the change in momentum. So ladies and gentlemen, you will be expected to draw such vector diagrams. Very, very, very important. Very, very important. Immediately at number 5, I can add velocity versus time graph. Why velocity versus time graph, ladies and gentlemen? Velocity versus time graph because we said most positive means right, left means negative, and then this is just now velocity. What do I know, ladies and gentlemen? It was traveling at 20 until it hits the wall. But when it hits the wall, let's go back. When it hits the wall, for it to change direction, what must happen? Your Excellency, for it to change the wall, what must happen? Can it change direction with the same velocity of 20?
No, sir. It lost some of its energy.
It lost some of its energy, so for it to change direction, it should actually come to 0. It must stop, ladies and gentlemen. And then once it has stopped, it means now it is changing direction and coming into the left hand side, that is now moving away from the wall, and it will now start immediately moving again with that velocity, ladies and gentlemen, of 15 meters per second and 20 meters per second. So actually here, okay, let's maybe do it this way. This section here, it is actually during the collision. Because why, ladies and gentlemen? It cannot be in a position of changing direction without actually saying the V here during, for that action pair reaction pair to happen, the Newton third law to take place. For it to happen, definitely that object must be stationary. You can never change your direction before you try to reduce your speed, lose some energy, and actually now have that 0. So remember, the plus here and the minus of the Cartesian plane, they only indicate direction. So when we get to vertical projectile motion, also the very same principle applies, because you have an object that is going up, coming down, so we only do what? We only have up and down, or right and left, as plus or minus depending on the information that is given. So ladies and gentlemen, I have drawn a velocity versus time graph for an object moving towards the wall, hitting the wall, ne? And then immediately changing the direction. Can we draw for momentum versus time? Yes, definitely we will be able to do so. Ladies and gentlemen, it is exactly 1856. I am going to pause it here, and then give you your 4 minute break, drink water, refresh, and join again at exactly 7 o'clock using the very same link, and then we will continue from here. With that being said, thank you very much. Let's meet now immediately in the next session.